Okay, so thank you very much for the introduction, and thank you very much for being here today. Good afternoon. And so today I will try to introduce very briefly the challenges that we encounter every day in the management of fisheries. So we try to explain very briefly what actually are the challenges in making better the use of exploited resources in the aquatic environment in general, but especially marine environment, with focus on the Baltic Sea and on the Baltic Sea cod, which is one of the most important fish species in the whole North Atlantic. So this is more or less the outline of this talk. So I will talk very briefly about fisheries management, what are the different level of complexity of the fisheries management. And then I will go a bit deeper in the challenges of the Baltic Sea, and I will try to explain a bit more in details two different main and big questions that we have, talking about the population structure of the different fish species with focus on the Baltic cod. And I will talk also about the changes in spatial distribution of different fish species. And then I will also touch the question of what management option actually we have to try to manage in a better way these species and this stock in the Baltic Sea. And then I will try to explain all of this in view of different projects that we have currently ongoing in our department on these subjects. So fisheries management. I don't know how many of you are familiar with this concept, but there are different steps or different level of complexity of fisheries management. So in the bottom there, we have the single species approach. So it means that we try to make different estimates of the status of different population in the sea, and then we try to say if the exploitation is sustainable or not, if the abundance of one species or one population in the sea is big enough or not. And then we have another level of complexity that we can call ecosystem approach to fisheries management, in which actually we consider this species or this population included in its environment. So we take in consideration climate variations, we take in consideration habitats, suitable habitats for these species, or we take in consideration also interaction with other species. So if there are a lot of predators on the species, if there are a lot of prey, and so on. And then we have a different level of this complexity of this management. And at the top of this complexity level, actually we have what is called ecosystem-based management. It means that the fisheries is only one very small part actually of the whole picture, and is only one sector that we need to try to manage in the best possible way. And this, of course, creates a lot of political questions and a lot of political troubles, I would say. So one of the main questions, actually, that we try to work with is if we actually use in the best way all the biological knowledge that we have on the fish species, on the interaction between species in the management of the species. The other, or a question that is inside this main question, is that what are the drivers actually of the change in the size structure of population and of fish community? So why we have changes in the size range, for example, of different fish population in time? And another very important question that we work with is actually what are the drivers of the spatial distribution of the fish species in the sea, and what are actually the consequences of this change in distribution. So just to start with and to try to introduce our focus area that actually is the Baltic Sea, at least in this species, in this speech, is just a simple representation of the Baltic Sea. So the Baltic Sea in the offshore part is have a very low biodiversity because it's marine area where we have many marine species, but the salinity of the Baltic Sea is very low. and this limit actually the number of species that can live in the open part of this sea. So these are the species that are most representative in this area. We have the cod, that is the main fish that is eating other fish. That is maybe the species that is the most important commercially in the North Atlantic, as I said before. But it has also a very key role in the ecosystem. And now actually the ecosystem is working. And then we have the main prey of cod, which are the sprat and herring. These are instead the two species that are living in the pelagic water. So they are not living close to the floor, sea floor as the cod, but they live more in pelagic water. And then we have the species that actually live on the sea floor, like flatfish, and like other organisms that we will see later on that are very important for the function of the ecosystem. Since the biodiversity is so low in the Baltics, it means also the interaction between the species is very strong. So if we take away one species from the ecosystem, these will have big consequences over the rest of the ecosystem, because the species cannot be substituted by another one, because there are not other species. So actually this is the main problem, or the main question that we would like to tackle. So this graph is showing the change in the size structure of the cod population in the Baltic Sea in time. So you see, for example, the situation in the beginning of the 90s, so we go back almost 30 years. You see that actually the cod population was constituted by small fish, but also quite a lot of big fish. For example, here you see that we had many fish that were above 40 or above 45 centimeter. And for being in the Baltic Sea, where all the organisms are a bit smaller than other areas of the North Atlantic, these are cod that are quite big. Instead, if we go in the last 3, 4, or 5 years, we see that actually we don't have anymore the big cods. So all the size structure of the population is just squeezed. So the population is made up of fish that are around 30, 35 centimeters, maximum 40. And this is a big problem from ecological point of view, because as I said, cod is one of the main predators for other fish species in the Baltic, but also for a commercial point of view. This line that I showed here is actually what is called the minimum landing size. So it means that the commercial fishers cannot land, so they cannot sell fish that are below this line. So you can see that back in time, actually there were a lot of fish that were allowed to sell. Nowadays, very small proportion of these fish can be sold to the market. This until 1 year ago. Now the new regulation took away this minimum landing size, so nowadays there is a different kind of problem. But at least until last year, you can see this big problem of the fishermen, that they couldn't actually find big fish to sell to the market. So one big question that we tried to answer in the last years has been always why we have seen this big change in the size composition of the species in the Baltic Sea. I can think about two main reasons, because we've seen this, to explain why we have seen this big change. The first one could be the fishing. So the fishing, is very eye selective. So the fishermen try always to take out from the sea the big fish, because they get, of course, more money for the big fish. You can sell them for a bigger price. So the first thing that I think about is, the fishing pressure is so high that actually the big fish are just taken out from the system. The second thought is that maybe the growth rate of each single fish has decreased. So actually the individuals don't grow quick enough nowadays. And this opens the room for two other questions. The first question is when, under the lifetime, actually this species has a decreased growth. And the other question is actually why the growth has decreased. And the main important question, or at least if we work in management, is if we can do something about that. to reverse the trend, to get back the big fish from the system, in the system. So what we look first is at the temporal change in different biological parameters to try to answer these two questions or three questions that I had before. So the most important or the easiest thing that we can look at to answer that question is to look actually how fast a fish grows. So actually if we have the age, so if we know how old fish are when we take our samples, and we can measure the length of this fish, and we can see how quick actually an individual grows. And then compare with all data to see actually if this curve has changed or not. The problem is that, so the question is that either the big fish, so the old fish, have disappeared from the system because maybe the exploitation has been too high, or the alternative hypothesis is that actually they start from the very beginning, so when they are very small. I don't see if there. They start already to be smaller from the very beginning when they are born, and they are not able to catch up during the lifetime. So that in the end, we have fish that are smaller in size at the same age. The third hypothesis is that actually in the beginning, they were growing with the same speed, but then at a certain point, actually, they are not able to grow anymore. That's why we don't have big fish anymore in the system. So actually, if we knew the age, and if we knew actually the mean length of this population, we could answer this question if they are the old fish missing, or just because the fish are not growing quick enough to reach big size. The problem is that to estimate the age of these fish, usually we use what is called otoliths. I don't know if you are familiar with this. Otoliths are ear stones or ear bones that are in the head of each fish. So each fish has 3 pairs of ear bones, one on the right side and one on the left side. And we use these otoliths to estimate the age of the fish. So more or less, the otolith is growing like a tree. So like is laying down one band each year. Usually this band I lay down in winter time. So actually by counting the number of these rings, we can come up with the age of the fish. The problem with this is that if we go back in time, it was relatively easy to estimate the age of this species. Nowadays, it became extremely more difficult. So we cannot see anymore all this clear band in the otoliths. We don't know why yet, actually, but we know that it has become extremely difficult to set age to each single fish. So the question remains, actually, since it's so difficult to determine the age of the fish, we don't know actually if is the growth that is decreased, or actually are the fish that die before they get big. So we cannot answer that big question. What is done usually when you want to estimate the growth rates and you want to also to estimate other biological parameters like migration and so on, you can try to tag the fish. So what is usually done, for example, for tuna, we use tag. So we use a small tag that is fixed on the back of the fish. You take all the measurement of this fish, the length, the weight, the other parameters, and then you put it back in the sea. And then you hope that, for example, our fishermen are catching back this fish after, I don't know, not too soon, because then it's difficult to estimate anything, but after some months, after some years, we get back the fish. And with this, we can just, measuring and weighting the fish, we can see, okay, this fish has been growing like 10 centimeters in 1 year. So we can really understand how quick the fish is growing. And then comparing this with old data that we have taken data from the 50s and 60s and 70s to see if the growth actually has changed or not. So this is a project that we are working on right now. And as I said before, this is a method that used in very migratory fish like tuna, for example, or sharks. When we want to follow the growth rate, we want to follow the migration of different fish. This is a method that is very useful. And this is the tag that we are using. So usually you put on this tag all the information that you want, like telephone numbers, like website. So when the fishermen are catching back this fish, they hopefully read what is written there. They call us immediately. We go there to get the fish, and we can make all our measurements that allow us to see if the fish is growing or not. Another possibility that we have actually to solve this problem of the aging is otolith microchemistry. This is a field that has used in the last years quite a lot to solve the aging problem of the fish. And for example, they have very fancy synchrotron in the Cornell University. There is also one in Switzerland, I think. And so this is just an accelerator of particles, so that make this particle running very, very quick and eating these ear bones at very high speed, and the ear stones emit radiation from that. And with that, we can estimate the density of different elements like calcium, strontium, and all different elements that the otolith actually has included. And we know that, or we think that these otoliths lay down different density of elements in a seasonal pattern due to biological cycles, also due to hydrological cycle during the year. So by looking at this seasonality of the density of different elements in the otoliths, we think that in the future we are able to age the fish in a much better way. So if tagging gives us a very short-term solution, so to tell us if the fish is growing or not, these methods will actually solve the problem of aging, so put an age to the fish based on the otolith. So there are different goals. One is just short-term, and the other long-term goal. But if we wanted to try to understand more about if the fish is growing or not, another idea that actually can be used is to look at the stomach content, so at the diet of this fish. Because the first thing that we can think of is, okay, if we believe that is the growth that has been changed, we should couple that with maybe diet. So to see if actually the diet composition or the amount of food that is ingested by the fish has changed in time or not. So during one European Commission contract that we have some years ago, actually we were able to collate a lot of these diet data from different institutes around the Baltic Sea to see if we could see some changes in time in the diet composition and energy intake from this cod. So we could get back data from the early 60s to nowadays. And this is very difficult, maybe, figures to understand, so I would like just you to focus on these three panels. Here you see just the proportion of different preys in the cod stomachs in different time periods. And you see, for example, that cod is eating nowadays more of these pelagic fish in the system than before. And what you see here, that actually is eating much less of these invertebrates that is living on the seafloor. So one big change that we see in the stomachs of cod is that they eat much less benthic animals, so these animals that are living on the seafloor and that are very easy to catch, and more on pelagic fish. And if we look, for example, at the timeline, at the time trend in the consumption rate, so how much they actually consume and how much energy they get in time, we see that, for example, for the small cod, in the last 10 years, they have much less energy intake than back in time. Instead, for the big cod, we don't see very big change. So we think that there are the small cod that actually are eating much less nowadays than before. And these create a problem for the growth when they are small, and they are not able to catch up when they are bigger. And this is another slide showing the same thing. So from a diet dominated by benthic invertebrates, we have now a diet that is more dominated instead by pelagic fish. And this we think that is why actually the cod is not growing anymore. So the question is why actually they eat less benthic food. So one big challenge that we have for the Baltic Sea is this problem of anoxia. So here you see the areas where actually the level of the oxygen on the seafloor is below 1 milliliter per liter, so almost no oxygen. And you see that area extent of this very poor oxygen condition water, it has increased a lot in the last years. And here's another photos or figure showing the same. So you see that the big volume of the water in the Central Baltic Sea is just dead. There is no oxygen and almost nothing can live there in this area. And this is not only a problem for the Baltic Sea, it's a worldwide problem. So in this area, the Baltic Sea, the Kattegat, on the other side of Sweden, we have a lot of problem with this anoxia. But also in other areas of the world, especially in the Gulf of Mexico, we have the same problem. And also in other areas like in the Japan Sea, stuff like that. So it's not only a problem for the Baltic Sea, but it is a worldwide problem. So we had a very big change in the ecosystem of the Baltic. So if we go back in time, we could see that cod could feed when they were young on these benthic invertebrates, and when they started to be big on pelagic fish. Nowadays, there is nothing on the seafloor if we are in the offshore of the Baltic. So it means that also the small fish needs to feed on pelagic prey. Another of ideas or hypotheses that we have for the slow growth of juvenile cods now is because they start to mature at the earliest size. So if we go back in time, cod started to be mature or started to reproduce, to produce eggs at the size of around 40 centimeters. Now they start to produce egg, so to reproduce around 30 or 25 centimeters, which means that probably now the cod is putting more energy to reproduction than to growth. That also can explain the decrease in growth rates. And this is a part also a bigger problem that could be due to fishing impact. So that the fisheries taking away all the fish that are reproducing later are changing also the timing of the reproduction of the cod. Then we wanted to look also at spatial distribution, spatial change in these biological properties. And what we see is that if we go back in time, actually the cod was distributed everywhere in the southern Baltic Sea. Nowadays, we have cod mainly in what is called Bornholm Basin, so it's the southern Baltic. So it's been a big shift from the distribution of cod from being uniform in all Baltic to be concentrated in the south. And if we look at one of the main prey for cod, so the sprat, we observe the opposite pattern. So back in time, it was more or less distributed in uniform way in the Baltic Sea, but now is mostly distributed in the north. So it means that we have a spatial mismatch from the predator, that is cod, to the prey, that is the sprat. So we don't have only change in time, but also we have a change in space. So actually what we can think of is this, what is the overlap actually from the cod to his main pelagic prey, that is a sprat. So what we try to estimate is what is the area in percent where is cod, where also sprat is occurring. And you see that here we have a big decrease in the last 20 years. So from more or less 100% to more or less 60, 70%. So in the area where there is cod, actually the sprat is not always occurring, but only in some areas. And this is what we call the predator perspective. So actually, what are the feeding opportunity of cod on this prey? And then on the other side, we have the prey perspective. So if we try to estimate the area we spread with also the predator is occurring, also this is decreasing. So from 100% to 60%, which means the spatial overlap between predator and prey became much, much lower nowadays. So predator and prey, they don't encounter each other anymore so much. So actually, this creates a big dilemma for the fisheries management, because back in time we had both cod and sprat, which both are very important from ecological point of view, the Baltic Sea, in the same area, or you could find everywhere in the Salton Baltic Sea, both species. Nowadays, instead, we have cod, as I said before, in the south, and sprat in the north, and they overlap in very, very small area. So one dilemma that we had in the last years that has been discussed many times also at the European Commission level is that if we should decrease the fishing pressure on sprat in the south, so actually to leave more food for cod in the south to grow bigger, and instead increasing the fishing pressure on sprat in the north, because we have a lot of sprat in the other area. That could sound a good biological advice, or good advice and management action for a biological point of view, but of course we need also to consider the political constraints. So if we implement a management like this, it would mean that actually to fish more of the prey sprat in this area and fish less in this area. So it means that, for example, fishermen from Poland and Germany and Russia that are concentrating their activity here, they should move much more north. This will create a lot of more costs, a lot of political issues, a lot of social issues. So actually this idea of redistributing the effort of the fishery in different areas actually has not been taken into account so far, but it has been considered anyway from the European Commission for the management of these resources. So just to summarize briefly what I present here today is that when we talk about ecosystem-based fisheries management, so include the inclusion of ecological consideration in the management of the different sources. This is already operating, so there are already different examples of this around the world. One example close to us is consideration of spatial management of sprat and cod in the Baltic Sea. It has not been used or implemented so far, but is always on the table when the politicians are discussing about these things. And then currently one major challenge is to try to actually to understand why we don't have big fish, big predator cod in the system. And we try to identify if it is a growth problem or it is mortality problem, because this will change in the way we want to do management. And one thing that I would like to underline very much is that actually nowadays we lack basic biological information to answer this question, so to tackle the management questions. Because for many years actually we based our calculation, our estimation of the population status on the age, so on the growth of the fish. But nowadays we cannot do any more because our aging methods is not working. So what we need to do is some very basic biological analysis to try to solve this problem before actually we can solve bigger problems that are related to ecosystem and ecosystem-based management. So actually I think this was everything that I wanted to show you here. And if you have any question, any discussion points, just to contact me and we can collaborate. Thank you.